pulling all this together, mentioned on that graph, the Earth has those 2 spikes versus the other planets have 1, and I said it's because of plate tectonics. We talked about mid-ocean ridges and trenches because of plate tectonics, different things. I keep saying because of plate tectonics. Well, we haven't always known about plate tectonics. Years and years ago, before 1960s, we had other explanations. The first person to get it close to right was Alfred Wegener. He noted that the coast of South America and Africa looked very similar. It looked like they could fit together like a puzzle piece. So he hypothesized that there used to be one big continent. He had a lot more evidence than just that. He did a study. He had fossil evidence. He had rock composition evidence. He had coastline evidence. He had a lot of evidence that said these used to be part of the same thing. And it even turns out his evidence was correct. They were. The problem was, he said, okay, there's continental drift. The continents drift around, they move. That's how it ripped apart. But he had no idea what would cause it. He had no explanation for how it would happen. Which means nobody would accept it. The scientists looked at what he was saying and said, sure, that looks neat. Those are some cool coincidences, but who can move a continent? Nobody can move a continent. They're solid rock, sitting in the middle, between oceans. The ocean floor is solid rock. This stuff can't move. Therefore, you're wrong. And that's how it sat until after he was dead. Poor guy never got to find out that he had almost all of it right. He even came up with the name Pangea. So he was the one who coined that term. I'm sure every single one of you has heard of Pangea. We now believe in Pangea. He was one of the only people to believe in it when he was alive. On the other hand, some people come up with their own ideas. Instead of continental drift, these guys came up with continental drip. They said, everything's pointy at the bottom, so it's all dripping. Of course, that's really bogus, but it's amusing. So, how did we finally figure out that Wegener was right? In 1960, a geologist named Harry Hess proposed seafloor spreading as the mechanism, as the explanation for this continental drift idea. And he based his seafloor spreading on paleomagnetics of the ocean floor. There are alternating bands of rock with stronger and weaker magnetic signals. So if you drive across the ocean in a boat, dragging magnetometer equipment through the water, picking up the magnetic signal, it fluctuates from higher and lower, higher, lower, higher, lower. That's this line up here at the top of this insert image. And then below is basically a cartoon showing areas of positive and negative magnetics in the rock. Now, those positive and negative magnetics in the rock add into the total Earth's magnetic field, and so his magnetometer behind his ship never picks up an actual negative magnetic field, but it picks up weaker because the Earth's strong field plus a little bit of negative in the rock results in a weaker positive field, or positive and positive results in a stronger positive. And they're mirrored on either side of the mid-ocean ridge. So on that crest, it's always positive right at the crest moving outwards for a while, and then a section of negative, then positive, then negative, then positive, and so forth. And he was able to figure out that this is because there were times in Earth's history where the magnetic North Pole wasn't up where it is now. It was actually down near our physical South Pole. So the magnetic pole can flip-flop. So anywhere that one of these white sections is showing on this little cartoon drawing is when the magnetic North Pole was down in Antarctica, or whatever was there back before Antarctica was there. And so that rock formed at that time and solidified with magnetic bearing minerals in that orientation. It's like you had a bar magnet and you froze it in an ice cube. It's going to stay in that orientation. So these magnetic minerals solidified into that solid rock, and they're stuck in that orientation. Then the magnetic pole changes, and the new rocks are in the other orientation. And so there's alternating bands. And they're moving outward from that ridge crest because it is spreading. As you create new rock, magma comes up, solidifies into rock, and it pushes away from the center further and further. It keeps filling in with new rock. And notice I said it's always positive in the center. That's because positive is defined as north is at the North Pole. That's where it is right now. Therefore, any rock being formed right now is going to be a positive. Therefore, at every single mid-ocean ridge crest, it is positive. And so, since these stripes were mirrored on either side, moving away, he was able to figure out, hey, you know what? We're creating land at the center and it's pushing away. This is going to move things. It's going to push the continents away from each other. And there's a big one of these rifts right along the middle between South America and Africa. So they were pushed apart. Wagner was right. The plate tectonics theory was born. The whole idea of tectonics was finally proven because of little magnetic minerals in the rocks in the ocean floor. And so you can see the plate boundaries here based on volcanic activity and earthquakes. All the dots are where there are earthquakes. And you can see the mid-ocean ridge going through the Atlantic Ocean. That's the plate boundary. You can see a boundary along here. That's the Antarctic plate to the Africa plate, the Antarctic to the American, Antarctic to Australian, Australian to Asian. Notice there is not a break between Europe and Asia. We call them two separate continents, but it is one tectonic plate, the Eurasian plate. There are some plates that are very small, some plates that are very large. And we know that because we're growing land at these, or we're growing crust at these mid-ocean ridges, we have to be destroying it somewhere else. And that's like on the other side of South America, there's a subduction zone. And the subduction balances out with the creation, and the Earth stays the same size. there are three types of boundaries, not just the convergent and divergent. The divergent is the mid-ocean ridges where we create new crust. Convergent is the subduction zone where we get those trenches and it consumes crust. There are also transform boundaries. This is where the crust just slides past some other crust. Nothing is created, nothing is destroyed, but it's not solid, it's sliding past each other. Most famous example is the San Andreas Fault in California. Out in the ocean, we've got all of it going on. We have a divergent boundary. Right here is a mid-ocean ridge, but sometimes the mid-ocean ridge is offset. It going along and then it jumps over 50 feet, half kilometer, whatever. When there's that jump, there's a little transform boundary. The land is sliding past each other. Because like up here, you can see that arrow showing moving away from the ridge. And down here, this arrow is showing that it's moving away from the ridge. So obviously, those two parts of rock have to be sliding past each other. Then over here, we have subduction. So yeah, it's pushing out. But this piece of land over here is being pushed from some other mid-ocean ridge. And so they're hitting each other, and one is subducting under the other. And that's destroying crust, equal to the crust being created at this ridge and the one off the screen. So a little closer look at the divergent boundary. You can see here this white is the asthenosphere. This gray and this are the lithosphere. And then up here this white is water. Closer look at a convergent boundary. Notice it's not just the crust subducting. The whole lithosphere. So the oceanic crust and the oceanic lithosphere are both subducting. That's important. That's something you don't want to forget, that both the whole lithosphere subducts, not just the crust. Right here is where we get our trenches, sometimes kind of shallow-ish like this picture, sometimes deeper, kind of depends how steeply this thing is subducting. And we get this here, this little flowery fan-shaped thing called an accretionary prism. What this is as this thing is subducting, it had all that pelagic sediment on it. It's getting scraped off and piled up into this accretionary prism. It's kind of like this land over here, this lithosphere, is acting like a squeegee and catching all of that sediment as this thing subducts and piling it up. We also get a volcanic arc a little ways back. This happens because as this lithosphere is subducting and getting deeper and deeper, it's getting heated up by that mantle it's getting plunged through. Once it gets hot enough, some of it melts. Melted material is less dense, i.e. it's buoyant, starts rising, and rises up through cracks because there's a lot of stress here. I mean, it's a subduction zone. Tons of stress. Rock diving through other rock getting bent, rock getting heated. Lots of stress. There are lots of cracks. This magma rises up through cracks, pops out to the surface. Now it's lava. Now it's a volcano. We have a volcanic, in this case, a volcano. But as we move out of the page or back into the page, there will be more of them. Therefore, it's a whole row of volcanoes, a volcanic arc. There are 7 major plates. We've got the North American plate, South American plate, African plate, Eurasian plate, Indo-Australian plate, Antarctic plate, that's our first 6, and then we've got our Pacific plate, there's 7. Then we have little ones like the Juan de Fuca plate, the Cocos plate, Nazca plate, Caribbean plate, Arabian plate, and so on. You can see this broken up line here is the mid-ocean ridge. The thick parts are the actual ridges, and then these thin cross lines are those transform boundaries that connect the sections of mid-ocean ridge. Another kind of collision zone is when neither plate subducts. For one of them to subduct, it has to be denser than the other one. That's what makes it go under. If they're the same density, neither one goes under. What happens? Well, what happens is kind of like a car wreck. You crash 2 cars into each other, and as long as one of them doesn't have a really pointy sports car type front end to dive under the wheels of the other one, normally they hit together and they just kind of crumple, and their hoods get buckled up, and the fronts of the cars are now taller than they used to be, but shorter side to side. They're compressed horizontally and extended vertically. Same thing happens to land. That's how we got the Himalaya mountains. India and Asia were the 2 cars. The Himalayan mountains are the crumples on the hoods of the cars. The two plates came together. They were both continental crust, so neither one was super dense, neither one subducted underneath, and they crumpled and pushed up and pushed down, and we have the Himalayan mountains and the roots underneath. Plus lots and lots of pressure, so lots of metamorphic rock. Rifting, on the other hand, is where it's trying to tear apart. Hasn't gotten as far as a mid-ocean ridge where it is tearing apart, but it's making progress. It's thinning, it's tearing. It's like when you have, Play-Doh or silly putty and you start pulling and it's stretching and thinning even though it hasn't broken in half yet. That's a rift zone. So it's rifting, it's thinning. The asthenosphere is getting closer to the surface. The upper surface is broken and jagged. Lots of faults. This is a rift zone. You can see the land on either side is trying to move away from that central rift area. If it's a failed rift, it's no longer pulling apart, but it is still thinner, and it's a rift scar. If it succeeds, it's going to create a new ocean, or at least a new sea. Probably not in your lifetime, probably not in your great-great-great-grandkids' lifetimes. It's slow, but it's going to happen. So what's moving them? Sure, they proved that they're moving using the magnetics in the ocean floor, but what's making it move? The first explanation was based on those mid-ocean ridges, saying, okay, they're convection cells. It's like boiling water in a pan. You put stuff on top of the water that's going to float. As it boils, and there's a hot spot and stuff comes up, and then it kind of billows out to the sides, it moves the stuff around. And they said that that was how the continents moved. They were riding on top of these convection cells. So the mantle's churning slowly, but churning, and the plates ride on top. The modern explanation says, okay, there's a super tiny bit of that happening, but that is not enough to move the crust around, to move the lithosphere around. What is doing it is ridge push and slab pull, and of those, primarily slab pull. Slab pull is kind of like if you have a blanket laying on your bed and you're down on the ground and you're pulling on the edge of that blanket. The part that's up on top of the bed is going to move. As you pull down, everything slides across the bed. In the earth, it's that part that has subducted getting pulled by gravity. It's denser than the mantle that it's cutting through. That's why it's actually cutting through, is it's so dense. It's like a big slab of something heavy sliding into the water. It keeps going through the water. It keeps pulling. Because the lithosphere is so thick, 100 to 150 kilometers thick, when that part is being pulled, it tugs the rest along with it. Ridge push is at that mid-ocean ridge. Your asthenosphere is pushing upward, and that dense rock that's forming that lithosphere is kind of on a hillside, and it's sliding down. Gravity's pulling it down, trying to slide down from that high ridge in the middle. That's ridge push. So in both cases, it's gravity. Gravity drives your slab pull. Gravity drives your ridge push. It's not so much the churning of the mantle where they're riding along from the friction underneath of that churning. That's a very, very small factor. So you can see here, this slab that's going down, you can definitely see how, hey, there's this huge, thick, heavy thing going down. Gravity's pulling it. It tugs everything along with it. Over here at the ridge, it's high. Gravity's pushing it downward. That's moving things along away from the ridge. So that's the ridge push and slab pull. On the other hand, there are things fighting against it, primarily friction. There's friction at the point of subduction as it scrapes past that other piece of lithosphere, which is, since it's scraping past, that's how it actually gets that accretionary prism, scraping off all the sediment. There's friction as it cuts through the mantle. I mean, the mantle is solid rock. There's a lot of friction to dive through it. There's friction at the base of the lithosphere as it scrapes across. So if, unless there happens to be churning at the same speed, then there's friction. And that's the end of this very long lecture for this week. But there was a lot to cover. We covered the whole Earth, inside and out. And hopefully it was a good first chapter in the new section. See you guys next week.